we're going to take this square piece of wire and surround it with a magnetic field in this direction, as we discussed yesterday. And I just want to derive a few things, because this links together mechanics and E&M a bit. So we're going to have to recall some of our mechanics. So this drawing is, I think, just about where we left off yesterday. We had a drawing like this, which I would say is top down. And then we had another version of it where we kind of turned it on its edge. Still magnetic field this way. Come on, draw those lines parallel, Mr. Shelton. Do a better job. Be a better teacher. I wish. But I appreciate your enthusiasm. And
that's not me, Ryan.
I wish. I was here till I was here late last night. Well, late is, I guess, arbitrary. I was here till about 8 last night. But having gotten here at 7:30 the morning, well, 7:50 the morning before, yeah, it was all about talking to parents about registration. I think the person left well, but I got abandoned there. All right, anyways, turn this on its side, and if perception is a thing. So if we're turning it on its side, I'm saying that the current on this wire is into the board, and the current on that wire is out of the board. I think it's a little different than what we drew yesterday, but it doesn't really matter that much. We know from our prior work yesterday that there's going to be a force along this wire that's downwards, right-hand rule, and a force along this wire that's upwards, right-hand rule. We okay with that? You guys checking it, making sure? I'm doing all my right-hand rule-y stuff right? Current, magnetic field. So extrapolating that to the other side, right-hand rule again if necessary, force is downwards here, and the force is upwards here. Yes, sir?
This is something else I just thought of recently.
Now, little things here, just little things. The size of each force is I, L cross B. Based on the drawing here, that would just be I, L, B. And the fact that it's a square, the substitution here would be I times S times B, where I represents the current in a loop, S is the side length of the square, and B is the size of the magnetic field. Everybody good there? Now, mechanics. If you don't remember this, now's a good time to probably brush up on it. Torque uses a lowercase tau as our symbol, and torque is R cross F. So for you guys who are in mechanics now, we haven't covered torque yet. This is a new topic. And I know I have a couple of you guys. So R cross F. R represents the torque arm, which is the distance from the pivot point to the point of application of the force. And again, if you guys don't remember this from last year, it's worth writing down. And F is just the size of the force. The cross product here has to do with the angle between the torque arm and the force. For the drawing that we have on the right, I hope it's clear that this object would probably rotate about its center, because we have equal and opposite force acting on either end. That's going to likely be the axis of rotation, which is going to make this our torque arm. And at this instant, only this instant, by the way, but at this instant, this angle is going to be the angle between the torque arm and the force. So for this moment, just like here, we're talking about this moment, this is going to be just RF sine 90 degrees. So we are looking at the moment that we have maximum torque. Now that is not going to stay that way for very long. The moment this begins to rotate, the size of the torque is going to be diminished. So it's not a big deal, but all motors have a point where you have maximum torque somewhere on their power curve, and you'll get a point where you have minimum torque. So we can bring these two things together. I hope you realize that we could talk about the net torque on the system. So this is that over here. Net torque is going to be equal to 2 times the individual torques, because there are 2 of them. And they are complementary. I want to say it that way because you should always check to make sure your torques are acting to turn your object in the same direction. Both of these torques are complementary. They are in the same direction. Now, you guys in mechanics and you guys in E&M, remember, torque obeys the right-hand rule. And therefore, the direction of rotation can be done using the right-hand rule. I don't know if you guys all remember that, but does this object rotate into the board or out of the board? You guys who had AP1 or mechanics should remember that the direction of rotation obeys the right-hand rule. If you don't, your fingers curl in the direction it's rotating and your thumb points along the axis in the direction of the rotation. So using the curl rule, this object's going to rotate into the board. That's what we think is going to happen based on the direction of the force. We can verify it using the 3-finger rule to figure out the direction of the torque. Torque is a vector. R, F, and then torque is your thumb. So R cross F into the board. R cross F into the board. So both of these torques are into the board, so the object rotates into the board. So, again, 2 torques, that's going to be 2 times R times F times the sine of 90 degrees. But R is 1/2 of a side length. So this is going to be 2 times 1/2 S times F. That good so far? So this is our net torque developed by our motor. Going one step further, we can sub in the size of the force, and we'll get S times IS times B. And then we get this IS squared B. And that's our net torque. You guys okay back there? Anything I can help clarify, or? So, going back here, this is it. And I want to point out what's important here. It's not obvious, but S squared is the area of the loop. It can be shown that regardless of the shape of the loop, the torque is based on the area. So it doesn't have to be square. We used a square because that made it the symmetrical portion of our calculation the same. But if you do this, even with a circular loop, you will end up getting the area of the loop here. Now, I'm not going to do that one because that involves having to actually integrate a line integral across the circle to get the calculation for the size of the force. And I don't want to do it, and I'd probably screw it up anyways. So if you're interested in the math on that, I mean, I'll be happy to walk down that road one day, but not today. But what we want to do is we want to develop our motors today. So I'm going to show you how to build a motor. There's a number of ways I could do this so that more of you get a chance to see, but I'm probably just going to do it at my teaching desk and have you guys kind of surround it. So if you'll give me a minute, I'm going to get set up, but we have like 6 people out. So I'm also going to set up a camera so I can just film my hands while I do it. so that those people can kind of follow along.